All right. So thank you, Marlies, for that, for your talk. It is up to me to introduce our next speaker. I'm very delighted to. She is our keynote speaker for the day. She came all the way from London. She started in 2009 at FEMRIP, where Marlies also collaborated with for her research, as a fellow at the Hand and Brain Lab in Oxford, and where she later on became a PI. And then in 2016, she picked up her lab and pushed it to London, where it is now the Plasticity Lab, where she is the head of the laboratory. She, as the name of the laboratory suggests, she is interested in researching plasticity in the brain and focuses on individuals with an amputation, specifically for the hand, and how they adapt to a prosthetic or lack thereof. And before I give too much away, I will just let her do the talking. So please welcome Tamar.
Hi guys, it is such a pleasure to be here today. As you're going to see through my talk, my lab is like hugely capitalizing from your MSc program. I have supervised 5 students from the Netherlands MSc programs over the last 4 years or so, and most of them have stayed in my lab for PhDs or RA-ships, and it's such a pleasure to work with such motivated, professional, driven and thoughtful people. So I'm a huge fan of your training program, and I hope maybe my talk would inspire some of you to consider spending a year in London. It's expensive, but it's worth every pound. So I want to start by sharing a vision of the future with you. A future where we would opt out individually to replace our own existing limbs, our legs and hands, with artificial limbs, providing us with opportunities to be stronger, faster, more agile, maybe increased dexterity, and according to this video, a lot sexier. So what I want to explore with you today is how this vision can actually fit into our brain and our current understanding of brain plasticity. So I want to start with this caricature of how different body parts are represented in the brain. It's the famous sensory motor homunculus, which is right here along the central sulcus. And bang in the middle, you can see this hand area, which benefits from some serious real estate. So it's just in the middle. It has great connections and it's huge. So we can actually zoom into this area, and what we find is that within the hand area there's also this really nice organization. This is specifically for primary somatosensory cortex, where neighboring fingers on the hand are represented next to each other on the brain, so that we have a hand map or a somatotopic map, which makes this area very accessible for research. Now, according to this vision I've just shown you, and this is actually the vision that is supporting current efforts for brain-machine interfaces, if we want to use artificial limbs, all we have to do is get rid of this hand representation and replace it with our prosthesis. So we're just directly going to plug in an artificial limb into the hand territory. Now, this vision is entirely contradictory to decades of research into neuroplasticity, where people have tried to see what happens to a territory in the brain once the major input to it has been removed. Let me walk you through one beautiful example. So this is a study by Merznick and colleagues where they took advantage of these detailed digit maps. This is in an owl monkey, and they wanted to know what's going to happen to this digit 3 territory if they're amputating the middle finger. And what they found is that only 2 months after the amputation, the territory previously associated with digit 3 has been taken over or subsumed by its cortical neighbors, digit 2 and digit 4. So if you lose the input to one part of the brain, cortical neighbors are taking over. Here's a more striking example. So this is from Pons et al. Here they've deafferated the entire hand and arm. So the area you see here in white, it's the hand and arm area. This is a macaque monkey. And what they wanted to see is if, they sit tight, they sat for about 10 years. There's an interesting story behind this, but maybe that's for the questions. So they go back many years after and they want to see what are the neuronal properties within this hand and arm area, the deprived cortex. They found that it is best explained by touching the monkey's lower part of the face. So the squiggles you see here are receptive fields for neuronal responses acquired from the previous hand and arm area. So based on this and many similar studies, it has been established that if you lose an input to one territory, the cortical neighbors are going to take over. And this is the textbook knowledge that we are currently working based on. So this is posing a really serious problem when we're trying to think about how are we going to interface with artificial limbs? Because if the hand area is taken over by the face, where are we going to stick the prosthesis? Okay? So today I want to walk you through this question: what happens to this area, the hand area, once it becomes freed up? And I'm going to take a fresh approach. Rather than studying the cortical neighbors as other people have done, I'm going to really take advantage of amazing people throughout the UK that have to figure out how they're going to live their life without upper limbs, without one or two limbs. And it could be because they were born without a limb, it could be because they lost it later in life. But the focus of my lab is looking at these people and how they solve problems, and let that inspire for us opportunities for reorganization. So today I'll walk you through some cool examples for alternatives to traditional hands. We're going to start with these guys. They were born without any hands, so any daily task that you would do with your hands, they would do with their feet. And in fact, the people we're studying are actually foot painters, so they can do stuff with their feet I could never do with my hands. Then we're going to move on to people that were born with only one hand. So they still have one hand that allows them to lead interactions with the world, but they need to support this hand the way you would do with your non-dominant hand. And for that, they adopt a range of strategies with the residual arms, as you see here, but also with other body parts. So we're going to walk through that. And finally, of course, artificial limbs. They are designed to substitute hand function, and we're going to see how they are represented in the brain. But before I walk you through all of that, I really need to start with probably the most common form of hands that we see in my lab, which are phantom hands. So if you lose your hand to amputation, the sensation of the hand is not going to go anywhere. Almost every amputee that lost their hand in adulthood would say that they can still feel the lingering sensation of the hand. And it's very famously painful, and we do a lot of research on that, which I would not share with you today. But it doesn't have to be painful. It's best described as the feeling that they can still feel the hand as being there. And interestingly, when you ask people to move their phantom hand, it doesn't sound stupid to them. They know what to do. And they actually describe very vivid kinesthetic, detailed sensations. So one person would say, I can kind of move my pinky and my thumb, but the other fingers are frozen. Another person would say, I can move each and every one of my fingers as easy as I can move the fingers of my intact hand. And I just want to show you an example of one person that can move their fingers easy peasy. This is Chris. He lost his hand about 25 years ago due to farming accident, and he has a low level of amputation. So he's amputated up to here, meaning the muscles normally controlling the hand are still intact. So what we'll do is we'll ask him to move his phantom fingers. He's going to do a thumb opposition task, so each of the fingers towards the thumb. And we're asking him to go through cycles, and we're asking him to count when he completes each cycle, so just we know what we're doing, because obviously he doesn't have a hand, okay? So you're going to hear him counting, and you're going to hear the thick Dutch accent of my student asking him to count. And I want you to pay attention to the screen in the background, because we are recording with EMG, surface EMG, muscle responses while he's doing this. And I also want you to pick at the stump, okay?
Okay, so real finger tapping, go.
1,
So you can see the burst of the EMG.
2, 3,
And you can see the stump moving.
4, 5.
Okay, so here are his 5 cycles. In each cycle you can see 1, 2, 3, 4 bursts for each of the fingers moving towards his thumb. And you can see a propagation in the intensity of the utilization of the muscle that we are using from one finger to the other. So there's a very organized output to the motor system when Chris is moving his phantom hand. And what I want you to take from this is that when we ask amputees to move their phantom hands, they're not just imagining they're moving their hands, they're actually engaging the motor system and they're actually sending signals, okay? So by the same idea, we can put Chris in the scanner. So these are very gentle movements. Here he's using his intact hand. You can see activity in the opposite hand area. Now you won't see much in the video, he's moving his phantom hand, but if you look at his brain, you would see his phantom hand showing very clear hand-like representation in the contralateral hemisphere. So we can take advantage of the fact that amputees can move their phantom hands to activate the missing hand territory to actually study what happens in the missing hand territory after amputation. So just a quick method scan. This is 7 Tesla imaging where we're trying to identify digit selectivity. So this is not an amputee, this is my Dutch student. She's in the scanner, she's moving her fingers one after the other. And we're using a technique called a traveling wave or phase encoding to identify selectivity for one movement compared to the others, resulting in this propagating wave of activity along the hang knob of the central sulcus. So we can now color code preference to each of the fingers, as you see here, between the thumb to the pinky. And you can see this nice dissociation for regions liking the thumb, the index, the middle, the ring, and a tiny bit of pinky. And there's two things I want to emphasize here. One is that this map is in the central sulcus and postcentral gyrus. So this is an S1 map. And this is because S1 is the only area with sufficient level of organization that allows us to pick up this selectivity. Now remember, these are selectivity maps. It doesn't mean that the rest of the brain is not activated. They're definitely engaging their motor system, so they would engage the motor cortex, the premotor cortex, so the secondary somatosensory cortex, and so on. But because there's no selectivity structures there, because there's no topographic maps, we won't be able to pick them up with this technique, okay? Another thing I want to point to you is how similar these maps are that we're getting with the 7 Tesla to those originally observed with the monkeys, okay? One more method slide. I want to convince you that it's not stupid of us to do what we're going to do next. So one thing you can notice here is just these are 3 random, almost random participants. I'm proudly at the top. I always put my brains first. And we're just using 4 fingers just to save some time. And you can see here representation of the index, middle, ring, pinky for 3 participants. And what I want you to notice here is that although there's obviously some regularity in the organization of the fingers, the location on the bank of the central sulcus, there's also a lot of differences between participants. And we needed a technique that we could actually use in individual participants. So we wanted to see if this variance is actually attributed to differences between people, or is it just noise? So we scanned the same participants over and over and over again for a course of a month. And what you can see here is that the specific details of each participant are very persistent across scans. So what I want you to take from here is that different people would have slightly different maps. They're not going to look exactly the same across participants, but it doesn't mean that they're noise, okay? So with that in mind, we're going to play a game which is called Which is the Missing Hand Map? So I've shown you a ton of these maps, hand maps so far. You're all, proficient neuroscientists. I'm going to walk you through 2 maps, and you're going to have to guess which of these 2 maps belongs to Chris's missing hand. This is the guy you've seen before, moving his phantom hands around, okay? So let's see. Here we see central sulcus, postcentral gyrus, with representation of the thumb, the index, the middle, and the ring. So no pinky, so it's an incomplete map. But beyond that, you can see very nice representation of each and every one of the fingers. Here's another map. So again, central sulcus, postcentral gyrus, thumb, index, middle, ring, and pinky. So this is a complete map, but the representation of digit 4 and 5 is kind of merged together. So there's no good separability across all the fingers. So raise your hands if you think that the left map belongs to the missing hand of Chris. All right. Raise your hand if you think the right one belongs to Chris. Okay, I should have told you that in the introduction. I'm sneaky. I chose the worst participant I've ever seen. So this is actually the map of Chris. So we can nicely see representation of 4 of his 5 digits, and actually if we waiver this criterion for multiple comparisons, we would actually see his pinky as well. And that's despite the fact for 25 years he hasn't had a hand. Now when we saw that, of course, we were thrilled, but as I've shown you in the video, Chris is able to engage his muscles. So it's true that we tend to think of these maps as belonging to the skin of the fingers, but through Hebbian learning, it makes sense that some of the contribution from the muscles would also be represented in here. So we needed another participant, so we found Mike. Mike also can move his fingers very proficiently, at least so he tells me. And he has a high level of amputation, so he doesn't have any more muscles that normally control the hand, okay? And here we scanned his right hand and his left hand. One hand is missing, one hand is intact. He's been amputated for over 30 years, and I should tell you that Mike doesn't use a prosthesis, so his intact hand is really the hand that he relies on for any daily task you can think of. So it's really overused, okay? So I'll walk you through the 2 maps, and we take another vote. Try to take in everything you may have picked up through perceptual learning in the previous slide, okay? So here is the first one. So here we have the central sulcus, the postcentral gyrus. We have very nice representation for the thumb, index, middle, ring, and pinky. Perfect map. Here's another one. So central sulcus, postcentral gyrus, thumb, index, middle, ring, pinky. Another perfect map. Which of these perfect maps belongs to Mike's missing hand? Raise your hand if you think it is the left one. Okay. You should also know that I like these feel-good moments at the end where everyone gets it right. Raise your hand if you think this is, yeah, good job, guys. You made me happy. So this is Chris's missing hand. Sorry, Mike's missing hand. The thing you are probably all picking up on is that there is less color in this map compared to this map, meaning there is reduced selectivity. So the selectivity is a bit reduced. But any other aspect of this map that makes this, the hand area, the 5 digits, the relationship between them, the overlap, all of them are exquisitely preserved. This is despite the fact not only that these guys didn't have a hand to move in the scanner, but also that they had not used this hand in decades. So Mike and Chris are with very, very vivid phantom sensations. They don't necessarily represent the entire population of amputees. So they would sit over here, whereas in a random group of 17 participants we recruited for a study, there's just as many participants that have very weak sensations. And we wanted to know whether this persistent representation of the hand, despite the physical loss of the hand, is an organizing principle or rather a correlate of phantom sensations. So only people that experience vivid phantom sensations get to have it. We couldn't scan people with 7 Tesla due to MRI safety limitations, so we had to come up with a technique that we can do with standard resolution, and we chose representational similarity analysis. For those of you that are not familiar with it, we are taking the voxels in the hand area of the somatosensory cortex. We ask participants to move each of their fingers separately, as we've done so far, and we ask how similar is the pattern across voxels when they're moving one finger compared to another finger. So this gives us this distances matrix here. So the greater the distance, the more distinguishable the patterns are. So that, for example, if we look at digit 5, it's going to look most distinguishable, highest colors, with the thumb and the index, and most similar to digit 4. To make it easy to visualize, we just project these relationships into a 2D surface. And here we have the representation of the thumb, index, middle, ring, and pinky. The further they are from each other, the more dissociated the patterns are. So that you can see that the middle finger, for example, is furthest away from the thumb and closest to the index and ring finger. So this gives us another way of looking at representation that is topographic, okay? So Here are our control participants showing very nice dissociation. So this is a canonical hand map. Now we studied two groups of amputees. One are congenital one-handers, they were born without a hand, and importantly for us, they don't have phantom sensations. The other is the acquired amputees. These are the people with the range of sensations I've shown you before. When we look at the congenitals, when we look at the dissociation of the patterns for each of their fingers, we're asking everyone to do the same thing, move each of the fingers that you don't have. We can't really see any dissociation across the fingers, so there's no unique representation for each of the fingers, so there's no hand representation in the traditional sense. When we look at the acquired amputees, and remember this is a group that is highly varied in phantom sensations, we can see that on average they show a very similar pattern to that in controls, with each of the fingers clearly separated from the others, and neighboring fingers that are closer to each other on the hand represented more similarly in the brain. So to summarize, there is a lot of persistence of hand representation that we see in the brain so long as you used to have a hand, and it doesn't seem to matter too much how much you can feel your hand. For example, when you move it, it's more about whether this topography has formed. But this is of course for people that used to have a hand, and we can ask the question, what about people that have never had a hand, or people that have never had any hand? So this brings us to our foot painters. This is Tom. Tom is a foot artist, so he makes a living out of drawing paintings, which he exclusively draws with his feet. His level of dexterity is remarkable. And he's one of the three foot painters in the UK, and we were lucky to recruit 2 of the 3 to participate in our study. Now, what do we know about foot representation in the brain? Honestly, not too much, probably not the most fascinating topic for an MSc. We do know from New World monkeys, those are the little monkeys that climb on trees, that they do actually have detailed representation of the toes. So you can see here representation of the pinky to thumb in a medial to lateral fashion, similar to the medial to lateral representation of the hand. So actually for these little monkeys, the representation of the hand and the foot is very similar. In humans, we seem to have lost this. So this is from our data, but there's another 7 Tesla study by another group showing the same result. This is our prettiest map that we could find. So we have here thumb, index, middle, toes, as you can see here in the color code, but it's not in the right orientation, and it's only 3 toes. So this is the best we got out of 18 attempts. These are more characteristic examples. You can't really find anything. So this is our group average. We can't find clear separability for fingers, or for toes, sorry, in the brain. In the toe artists, of course, we would expect to find some exaggerated input going into that area that is quite specific for individual toes. So we were expecting that maybe in toe artists we'll be able to see some representation that is hand-like, that is topographic. And of course, since they don't have a hand and they don't have a hand map, we wondered if we could find some representation of their feet and their toes in their missing hand cortex. So here is the right hemisphere opposite to Tom's left foot. We're looking from the top, so this is the central sulcus, this is where the foot representation is, and we can blow up this. As you can see here, we can nicely see separability for his big toe, second toe, third toe, fourth toe, and we're still debating if this little speckle here counts or not. And importantly, the organization, the order of the 5 toes is exactly the same as documented in the monkeys. Here's our second foot painter. So he's a right foot painter. We're looking at the left hemisphere. And again, we find this beautiful medial to lateral representation for digit 1, 3, 4, and 5. So these are univariate contrasts, which are threshold quite heavily. Another way of looking at it is with representational similarity analysis, the technique I've shown you before, which is more sensitive. So if you guys remember, this is how a hand representation looks like when we look at it with this technique. And we wanted to know how hand-like the topography of the foot looks like. So here are our 2 artists, artist 1, artist 2, where you can see there's very nice layout of neighboring toes next to each other in this typical crescent-like representation. Here are our controls with the standard errors showing quite a bit of overlap across these representations. So we can quantify this by asking how similar each of these are, and for each participant, each control participant, to this canonical representation. And what we find is that controls, these are standard deviations, and the means don't show much hand-like features, but for our artists, we are between 0.8 and 0.95, I think. So we have very, very high similarity, so that the foot representation in the foot area actually looks hand-like. What about the hand area? So here the results are not as clear-cut and beautiful. So again, we're doing representational similarity analysis. We're getting these patterns. To my naked eye, this doesn't look a lot like this at all. Here are the controls. So again, doesn't look like this at all. So let's stats be the judge. So how similar each pattern is to the canonical head representation. And for the controls, we are around noise, so there's just no similarity in the representation of the feet in the end area. We're just looking at noise, to be honest. Here are our artists, so they're around between 0.4 and 0.5. So they're showing some hand structure for their feet in the missing hand cortex, but it's not as clear-cut, I think, as I've shown you before. So I guess this is one of these glass half empty, glass half full situations where you get to choose how you want to interpret these findings, whether they have some hand representation for their feet in their hand area, or if this is not sufficient. But the one thing I think we can take away from this study is that topography is a thing. So this raises the question, do you really need a structure, a body structure that has 5 digits in order to represent things like hands in the brain? And to address this question, we took advantage of the fact that people that only have one hand adopt a very rich repertoire of compensatory strategies, where some people would rely on their residual arms, others would rely on other body parts. Let me walk you through some examples. So here we have a person trying to open a bottle of water successfully opening a bottle of water by holding the bottle with his residual arm. Here we have also a person using his residual arm. He's using it remotely because he's using it to activate a myoelectric prosthesis to hold the bottle. We'll get back to that later on. Here's another person. He has a prosthesis, but this prosthesis would be useless for holding the bottle. So instead he's taking advantage of his feet. And here we have a person who's using his hand to hold the bottle and his mouth to open it. So from looking at the behavior in naturalistic settings, we established that all of these body parts are used for compensatory strategies. The residual arm, the mouth, and the legs, but not the intact hand. And this is because they're using the intact hand the same way you would use a dominant hand, so they don't use it to substitute the hand that is missing. So we can now ask whether those body parts are represented differently in the sensory motor cortex. So we're going to start with the residual arm. So what we ask the participants to do is just to move the residual arm in the scanner, and we have one-handers and we have controls. Here I'm showing you whole brain contrasts for the opposite hemisphere. Nothing happened in the ipsilateral hemisphere. And orange means that there's increased representation for one-handers compared to controls. The greenish thing you see in the back is our approximation of where the hand area should be. And here I'm showing you a region of interest analysis. So we're just looking at how activated the area is. And this is specifically the missing hand cortex when people are moving different body parts. So for the residual arm, you can see that within and around the hand area, there is increased activity in one-handers compared to controls. So when they're moving the residual arm, they're actually activating the missing hand cortex more than controls. Now, this is nice, but it's also a bit of a not great cue for us, because the residual arm is a cortical neighbor of the hand. And if you remember, all the theories from the textbook tell us that the cortical neighbors can benefit from the freed up territory. So it doesn't really tell us much about usage. This could just be spontaneous reorganization, right? So it's more interesting to look at body parts that are further away from the hand in terms of the homunculus representation. So here we're looking at the mouth. So participants are moving their mouth in the scanner. They're not manipulating objects, they're just moving them, blowing kisses in the scanner. And as you can see, within and around the hand area, there is increased activity in one-handers compared to controls. So again, they are able to activate their hand area when they're moving their mouth. This one is the feet, another representation that is further away, miles away, 60 millimeters away from the hand. And again, relative to control, we see increased representation for the feet in the hand area. What about the intact hand? The intact hand would share many neural resources with the missing hand cortex, so it would make sense to see increased representation. But if you remember, they don't use their intact hand for compensatory strategies. And accordingly, we don't find difference between one-handers and controls for that body part. So to summarize, those body parts, the residual arms, the lips, and the feet, show relative increased representation in one-handers compared to controls. We ran this study 2 more times with 2 other groups of one-handers, which were slightly overlapping in representation, just to kind of convince ourselves that this is a real result. And as you can see, there's nice replication and re-replication. Each of these body parts show increased representation in the hand area in one-handers, but not the hand that is not overused, okay? We also ran the same analysis in the cerebellum. The cerebellum is interesting, is that it doesn't have a tidy homunculus like in the cortex. It has a much more fractured representation, and the relationship of different body parts is different from cortex. But despite the fact that the topography is different, the results are the same. For the residual arm, for the mouth, for the feet, there's increased representation in one-handers compared to controls. So it really seems that whichever body parts are being used for substituting the function of the missing hand benefit from representation in the missing hand cortex. Now, one interpretation for that is, oh my God, so much plasticity, right? Another interpretation I'd like to introduce to you is that maybe we got the whole homunculus story a bit wrong. Because we tend to think of the homunculus as the representation of the various body parts, right? But what if it doesn't represent the body part itself, but instead the functions that are normally carried with that body part? So for the hand, it would be feeding ourselves, supporting the other hand, whatever you guys like to do with your hands. But this would involve, a complicated network of areas that are interconnected, which probably is why the hand area is in the middle of the central sulcus to begin with. So for these people, if their hand functions are fulfilled with their stump, with their mouth, with their feet, maybe this is not plasticity. Maybe it's just changing in input. So I don't have any way to support this theory. I just wanted to give it to you, okay? So going back to our working hypothesis, any body part that is being used to substitute the hand function could potentially benefit from increased representation in the territory of the missing hand. So this begs the question, what about artificial limbs? Artificial limbs, by definition, are designed to substitute hand function, right? So I'm going to show you the first of many studies that we're currently running on artificial limbs. And the video that you see here is by Steve, who is what I call a super user. He's just remarkable. The things that he can do with his prosthesis are just really, really impressive. Unfortunately, he doesn't represent most of the amputees population. Most amputees can only use their prosthesis so much. Now, the prosthesis that you just saw, it looks really cool, but the principle for operating it is actually very simple. It's a myoelectric prosthesis. So you operate your muscle, a particular muscle that has an electrode on, in order to open or close the prosthesis. And this is the same principle for myoelectric prostheses since they were become available in the early 80s. Let me show you another person using myoelectric prosthesis. He's been using his prosthesis for as long as Steve has. It just looks a bit different, but it's really the same type of prosthesis. And here I'm asking him to sharpen a pencil. Look how much he's struggling to steady the pencil, he has to opt out, which is why he's pressing a button all the time. And this is probably a much more characteristic usage of a myoelectric prosthesis. So myoelectric prostheses are operated by the muscles. They are probably the minority for users in terms of what people like to use. Most people prefer more traditional prostheses, which are the hook and the cosmetic. So let me show you a hook user sharpening a pencil. For the hook, grabbing and steadying a small object is no trouble at all. But what you can see is the way he uses his prosthesis is very, very different from the way we would use our hands, right? Okay, so moving on to cosmetic prostheses, those are designed specifically for aesthetic purposes, but in the right hand, they can be incredibly functional. And in fact, most amputees prefer using them. So they're not operable, but they are functional, okay? And what I want you to take from this demonstration I've just given you is that how useful, how functional the prosthesis is not in the hands of the designers. It is really up to the individuals, to the amputees, to figure out how to make most of the device that they're getting. So with that in mind, we wanted to know how individual people represent their prosthesis in the brain. And up until now, we've been exploring this wonderful structure, which we call the homunculus in the primary sensory motor cortex. But this is by no means the only brain area that likes hands. And I want to devote your attention to the occipitotemporal cortex, to visual cortex, where both us and others have shown that there are areas that respond more strongly when you show people pictures of hands compared to other body part or object categories. So there's actually a type of homunculus, if you label it, if you color code it by preference, as I've shown you before for the fingers, with the areas in yellow, these are bilateral areas that respond more strongly to images of upper limbs, okay? So that provides us with a very simple essay to try and determine how prostheses are represented in a hand area, because we simply show people pictures and see how this hand area responds. So we're going to show amputees and congenital one-handers, so people that use a prosthesis in daily life. We're going to show them images of upper limbs and objects, and this is just to allow us to identify these hand-selective regions, which you can see here on one example participant. And then we're going to show them pictures of prosthesis, and we're going to show them a range of images. These could be cosmetic prostheses, so the ones that are designed to look like a hand. They could be functional prostheses, which are predominantly these hook-like devices. And we've actually also taken pictures of their own prosthesis that they brought into the study and showed them the picture of the prosthesis that they actually tend to use. And we also asked them to bring friends and family to the study. So our control participants were people that are very used to seeing prostheses but don't actually use them. So with you today, I would only focus on how the amputees are behaving. So I'm going to show you here, for each individual participant would be one dot, and for each participant I would show you how much they were able to engage or activate the hand area, the visual hand area, when I showed them a picture of a prosthesis. And I'll show this under two conditions. When we're showing them the picture of the prosthesis that they know and love or hate, and when we're showing them a picture of another person's prosthesis. And just to make it interesting, because we are in visual cortex, I'm going to show you results from these hooks that don't look at all like a hand, okay? And I'm going to plot the activity depending on how much people use their prosthesis in daily life. So you want to know if the way you use your prosthesis means anything to the brain about how the prosthesis is represented, okay? And in both cases, we find the same relationship. The more you use your prosthesis in daily life, the more you're able to engage this area that has been developed to be a hand area for representing, at least visually, an artificial limb, okay? And it doesn't matter, it doesn't matter if it looks like a hand or not. It doesn't matter if it's a prosthesis that you've used before or not. It really seems to be a categorical representation of prosthesis. We also looked at how much these visual hand areas are corresponding with, through functional connectivity, with the missing hand sensory motor cortex. And again, we find that the more you use your prosthesis in daily life, the stronger the communication between the missing hand cortex and those bilateral visual areas. So using a prosthesis doesn't only locally affect how information is processed in visual cortex, it actually determines whole brain functional connectivity across networks. So from this study, it appears to us that there's no bottleneck in terms of brain representation to being able to represent a prosthesis. It seems to be up to usage. So to summarize my talk so far, if you ask any student who's taken a course on somatosensory cortex or brain plasticity, what is the determining factor for brain reorganization, they would tell you that this would be the cortical neighbor, so that the organization, the architecture in a given brain area or given brain network would determine opportunities for reorganization. From accumulating results in my lab, we actually think that it is anything but that. So we really think it is the input that is driven by daily behavior or persistent inputs from a lifetime of experience that would determine how organization occurs. So the first thing I've shown you is that there is a lot of persistent representation of the missing hands that really hasn't been factored in so far in any attempts, for example, for brain-machine interfaces or other opportunities for taking advantage of representations for rehabilitation. I also showed you that the same territory, at least in one-handers, can support a multitude of body parts so long as these body parts are used to support the function of the missing hand. And eventually I showed you what I like to call embodied technology, the idea that you could actually take advantage of a brain area that has been developed to support the body in order to represent an artificial limb. And as I said, this is just the tip of the iceberg in terms of our research. If you want to hear more about any of these ideas, there's two recent opinion papers that I've published last year, one about embodiment and the other about plasticity. So I invite you to look at these if you're interested. I just want to finish by thanking the many, mostly Dutch people that have supported this research that I've shown you today. In particular, Sana Kickert, who ran the studies about persistent representation, Dan Wesseling. I'm now realizing that now you know how bad my pronunciation is. Okay. Dan has done persistent representation and the topography together with Harriet Dempsey-Jones, who has dated for many years a Dutch guy, so I think we're consistent. The lovely Fiona Weiden-Heiligenberg, I'm very happy I can pronounce that, has run together with Tanya Orlov from the Hebrew University the studies on prosthesis, and my collaborator Avital Chachami at the Weizmann Institute, who looked at compensatory strategies. Thank you very much for bearing with me.
All right, so I think we have about 10 to 15 minutes for questions now. So if there are any questions. Sure.
Can you quick go back to the slide with the plasticity and embodiment article?
The functional connectivity or this one?
No, just the article to read.
Oh my God, animation, hang on. It's in Nature Biomedical Engineering. Here you go. But that's not a question. Ask me a question, come on.
So you were talking about how the freed up area can be used for different purposes depending on what you use it for, like to be your neighbors or prosthetic if you use it for that.
As a working hypothesis, right?
Exactly.
Yeah.
But what if the area you haven't been using a prosthesis for like 20 years and has been taken over by the neighbor? What then if you try to use that for that prosthesis? Can then that area be reversed to be used for something else? Is that possible?
So if you remember, I showed you early on in the talk that amputees, acquired amputees, have persistent representation, and it doesn't matter how long they've been amputated for, and it doesn't matter what their compensatory strategies are. So I do strongly believe there is an interface that people haven't necessarily been capitalizing on in order to interface artificial limbs in a rather intuitive and simple way. But it is up to me to try and understand why is it that this process doesn't happen naturally. The fact is that more than half of the amputees would not use a prosthesis regularly. For many years, people thought the bottleneck is technological. The prosthesis is just not good enough. But it is a fact that given the same prosthesis, one person like Steven, my super user, can do amazing things, and another person would kind of play around with it for a month and give it up. So this is something we're now studying. We're now studying super users. So we're actually recruiting people from all over Europe, including Netherlands, for those people that can just do incredible stuff with their prosthesis, and we're trying to understand what do they have that, you know, that makes the prosthesis so useful for them. So it's an open question.
So I have a question about the representations in the cortical map of the different fingers, for example. So do you know what happens if you ask to the control groups, instead of moving a finger, just to imagine the movement?
Yes.
Okay.
So we've run this as a control condition, both in the amputees and in the controls. So I can tell you that for the amputees, when we ask them to imagine moving their fingers, nothing. And the reason we use that as a control, and the reason we were interested in that, is when you try to speculate, how the hell are they activating their missing end cortex? Because, you know, we use people with brachial plexus injury that don't have any inputs from the periphery. And our hypothesis was that they're using efference copies. So the motor system is thought to signal to the somatosensory system predictions about, you know, what touch they should expect, what input they should expect. And even though we're using 7 Tesla imaging, we can't tell the layers apart. So we thought that if this is really due to motor planning, we should be able to see the map coming to life when they are engaging the motor system, but not see it when they're imagining. The reason I don't want to make a song and a dance about it is I think imagery is a very, very tricky task to give participants, because I don't have control. I don't know what exactly they're doing. We try to kind of, you know, insinuate in an ethically acceptable way that we can see everything they're thinking and doing, but I don't know if that's enough to get them to actually do the task, right? So that's our confound.
And the control,
They show very, very, it's, you know, it's, if you threshold, you don't see anything, but if you go, is there anything there, then there's, for some participants, like a tiny, tiny bit of selectivity. They're definitely not significant, but the structure seems to be there.
Two different amputees have different precision in the representation of their hands, and how is this related to the use of prosthesis? Can they, with this more, like, can they use it better with more hand-like prosthesis if they have the more specific hand representation?
Yeah.
And also the other way around, maybe they can use the hook better if they don't have this very hand-like representation anymore. Their relationship.
So we have a simple measure for how much hand they have by basically, you know, how much distances we find across the fingers, and we correlated that. We tried to correlate. We were very careful to only suggest, you know, 3 correlations, because I don't like fishing. And if you try any clinical or demographic detail we have, you will come up with spurious results. And I have to say, your question makes a lot of sense to me, but we didn't think about it, so we didn't look at correlation with prosthesis at the time. What we looked at is phantom pain, vividness of phantom sensation, and kind of how separable, how many fingers you feel like you can move. Because I told you, some people feel that they can move all of them, other people feel like they can move 1 or 2. And that is the only one that correlated. So the more fingers you can move, the more separable the representation is. But I think this is almost a testimony for their ability to carry the task. The better able they are to carry the task, the nicer the results were. Does that make sense?
Well, I'm not really familiar with this research topic, so as clear as can be. Thank you.
Have you already used electrical stimulation techniques to increase the plasticity, and is there a rate of success in there? What
would you like me to stimulate?
For example, the region where the hand nod is with RTMS, randomized.
Okay. Oh, so you don't mean the periphery, you actually mean direct stimulation. So you would suggest that I stimulate the brain while people are using their other body parts, for example?
Yeah, or previously to the training, to increase the training's effect.
We've done, okay, I'm going to give you an answer, not to your question, because we haven't tried your suggestion, but we have tried non-invasive brain stimulation to treat phantom pain. So what I've not shown you today is that the persistent representation actually plays, at least in our results, a major role for phantom pain. People that have more phantom pain show more, not more organization, but just more activity in the territory of the missing hand when they're moving their hands about. And what we think is the reason for that is phantom pain comes from peripheral ectopic firing. So basically there's junk information coming from the periphery through the C fibers, but also affecting the A beta, the myelinated fibers, contributing to increased representation and increased pain. And what we've tried to do is try to dampen that down or normalize the representation of the hand with TDCS. It was incredibly successful. A single shot of TDCS gave lasting for at least 1 week pain relief in people, and we ran it as a double-blind placebo-controlled study. But looking at the result, we ran the whole study in the scanner, so we gave the stimulation in the scanner. We realized that we targeted the wrong brain area. We looked at the territory of the missing hand, where all the interesting results were happening in the insula. So rather, my recommendation for the future would be focus on the insula and not on the missing hand cortex if you're interested in treating phantom pain, which you're not, because that wasn't your question.
I think we have time for 1 or 2 more questions. In that case, I have one myself. Oh, sorry. Go ahead.
You already mentioned the topic, but just wanted to ask you. If you compare those with who were born without a limb and those who acquired using them, what is the major difference between them that one has phantom limb pain or feelings and one doesn't?
What makes it so that some would have, that the acquired would have phantom sensations and pain and the congenitals wouldn't, you mean? I would say to have a map, any map in the brain, to have a coherent representation so that you could potentially have, the experience of having a body part. I think it needs to be formed during the critical period of development. So the people I showed you, their hand never developed. It might look a bit different if they had a hand and lost it in the womb. But if you've never developed a hand, you will never develop a map. And I think for this reason, you will not be able to develop sensations of the hand. Phantom pain is a bit different. I am a strong advocate of a peripheral origin for phantom pain. I'm a big opponent of the maladaptive plasticity theory, suggesting that phantom pain is due to reorganization for many, many reasons that we don't have time to go over. But I love to stick up my soapbox, get on it, and explain. But I think phantom pain is a lot more simple than we thought it is.
And regarding the stimulation in the critical period that you said, is the critical period still in the womb, or is it later?
We don't exactly know. It definitely starts in the womb. We don't know how long it extends for. In humans, in somatosensory cortex, it would be reasonable to think that it extends beyond the womb. So going to my toe painters, I think maybe in the womb we were all developing these toe maps, but maybe when we got out of the womb, our parents gave us socks and shoes, which made us lose these maps. Whereas, you know, if your baby doesn't have hands, you probably let him do more things with their feet. So I don't know when it ends, but it definitely starts in the womb.
Thank you.
One more question.
Yeah, I was wondering if you didn't develop during this critical period, is it possible for these people to ever use these kind of prosthetics that operate on a brain?
So there's two ways to use those prostheses that operate through direct brain-machine interface. One is through what the developers call a biomimetic interface. So the idea is that you take advantage of properties that are already in the brain in order to very intuitively control an artificial limb. The other one is through brain plasticity and learning. So you can just, at random, assign a function to a neuron, and through trial and error and reward, the brain eventually would figure out which neurons to read out from in order to achieve the goal. The main difference between these two approaches is one requires many, many months of training. We're talking about, you know, monkeys working, you know, every day, a couple of hours every day for months. And I can tell you from the prosthesis users that they don't like training. And, you know, like any gadget you would buy, if it doesn't work out intuitively, you're gonna give up on it, which I think is why we should try and fight for more biomimetics. So I think anyone would get a solution eventually, but we probably need to focus on different designs for acquired and congenital users.
All right. If people have any more questions, are they free to
Yeah, of
address
course.
you more? Okay,
Yeah,
great.
definitely.
So if you have any more questions, feel free to talk to her while we're having coffee and cake now. Just a quick reminder that you can still vote for the posters outside. And I think in the booklet it says that the discussion and the next talk will be across the hall, but we will be doing it here due to capacity limitations. So see you in a bit.